Hello, my name is Kayla, and this is my team's proposal for a mission concept design for SOLACE, the Solar Observation Laboratory for Active Warning of Coronal Expulsions. So in this presentation, we will go over why this is a necessary mission, defining the problem of solar weather and why we need early warning, establishing value, and then going over some alternatives and evaluating those, and then going into our own mission concept, and then some risk assessment at the end.
Hi, my name is Micheline, and I'll begin this presentation today by establishing why it is important for the future of space exploration that we begin this initiative of SOLACE. One of the greater and more misunderstood risks associated with space travel and space exploration is something called space weather. Space weather is generally solar activity that is released from the sun and propagates to the space surrounding the sun and impacts different bodies around the sun, including Earth, satellites, and any other spacecraft that might be orbiting around the sun. These solar expulsions can take form of plasma, radiation, radio emissions, and can impact Earth's magnetosphere and any of the electronics or even the physical aspects of satellites or spacecraft around the sun. This is important because in order to create safe missions with minimized risk for any future crewed missions to places like Mars or the Moon, it would be important that we understand how the space weather impacts our spacecrafts and the people inside of them. While there are many different kinds of space weather, the four shown on the screen are generally considered most impactful to our satellites and to Earth. Particularly, coronal mass injections and solar flares are responsible for releasing plasma and radiation into the space surrounding the sun, and when interacting with Earth's magnetosphere can cause geomagnetic storms, which are responsible for satellite blackouts and other communication issues. In addition, solar wind is responsible for creating extra drag on our satellites and spacecraft. All four of these things are types of weather that we would like to greater understand through SOLACE to be able to mitigate the risks associated with them. I've already mentioned the different kinds of communication impacts these solar expulsions and geomagnetic storms can have on a satellite or spacecraft, but the release of plasma and radiation can also have physical impacts to a spacecraft by causing surface erosion or degradation of the thermal properties, in addition to increased satellite drag. The plasma and radiation can also have effects on the power systems of a satellite by causing degradation of electronics or the surface charging or the use of the solar cells. So, in order to have successful and safe future space exploration missions, particularly for ones that are controlled by humankind, it is important that we understand how these different types of solar weather can impact our spacecraft to make them more safe and mitigate the risk for future missions. For this initiative, we have identified three key stakeholders, the first being the government, including NASA and any Space Force and military powers. The second being researchers, particularly the National Academy of Sciences, who initially started this initiative, and last being any commercial space companies that are interested in space exploration. From our key stakeholders and their perspectives, we've derived these customer requirements to ensure that our spacecraft can reliably capture weather data and continuously communicate it back to Earth and any future Mars missions per the National Academy of Sciences Heliophysics priority investigations. Currently, there are 3 heliophysics missions that are active and collecting heliophysics data. However, all 3 of these missions lack the ability to communicate any sort of early warning system to any future crewed Mars missions, which is a large part of what our satellite SOLACE will be responsible in doing. Next, we will get into the specifics of the problem and how we intend to solve it with SOLACE. The overall mission goal of SOLACE is to create a system that is capable of accurately measuring heliophysics data and reporting it back to Earth. And in addition, it should be able to process this data on board and send any proactive warning signals to any Mars missions that are launched in the future. Based on the customer requirements and the various challenges associated with launching and sending a satellite into space, here are the mission constraints that we expect to encounter when creating SOLACE. As seen in the CONOPS, there are 3 phases associated with SOLACE's mission. The first phase consists of launching SOLACE via the launch vehicle and deploying it into space, where it will then use its thrusters to perform orbital maneuvers and put it into the correct orbiting position around the Sun, where it can measure space weather data. Phase 2 consists of actually measuring the space weather data and communicating it back to Earth and to any future crewed Mars missions for the duration of its lifetime. Finally, at Phase 3, when SOLACE is finished with its mission, it will be sent into the Sun to collect any final data that it can as it gets closer to the Sun before it's destroyed. These steps are outlined in the functional analysis and architecture tree shown below, starting with surviving launch and ending with terminating mission. To organize all of our functional and customer requirements and ensure that SOLACE would meet every single one of these requirements, as well as being competitive in the industry, a QFD was created and analyzed for our mission. This is a list of the customer requirements that are mostly derived from the National Academy of Sciences Heliophysics Priority Investigation Initiative, which is the primary reason for beginning this SOLACE mission. In addition to the customer requirements, the team derived various engineering and characteristics and functional requirements that are necessary for the function of a satellite, particularly one that is measuring heliophysics space data and able to communicate it to various locations. Another important aspect of our QFD is the competitive assessment, because there are already 3 satellites in space measuring heliophysics data. We want to show why it is important that we have our specific spacecraft out in space measuring heliophysics data as well. This includes of a competitive assessment of how well our satellite will satisfy the customer requirements compared to the competition, and also a technical competitive assessment on how our spacecraft will satisfy the functional requirements in comparison to the competition.
Hello, I'm Mark, and I'm here to establish the value for the SOLACE mission. To ensure that SOLACE meets every requirement, we have developed an in-depth set of customer requirements, which are implicit and explicit, derived from the AIAA design paper, that go through the communication requirements, the solar weather monitoring, the mission budget, timeline, and things like surviving the launch and the different structures and maneuverability that's required to complete the mission. In the QFD section, we discussed how we derived functional requirements from the customer requirements. And so these, again, go into more depth about what sort of temperatures, radiation, environment the spacecraft needs to survive, as well as different criteria to evaluate the attitude control, the positioning accuracy, things like the propellant mass providing the right amount of delta V for the spacecraft. All of these things converge to ensure that SOLACE will meet the entire mission. And here is a hierarchy of the requirements. We can see we're breaking it up into 8 major groups based around the positioning, the imaging payload, the communications, the mission requirements, the power system, the structures, the developed technology, and the propulsion system. From the requirements, we derive a set of metrics of evaluation. These are just the high-level metrics. There are lower and finer sub-levels of each of these metrics, but we compare them against each other to find an uneven distributed weight to apply to each metric, so that way the highest priority metric is prioritized in the design process. We can then use these metrics to compare and evaluate different configurations that are proposed solutions to the design problem. The SOLACE spacecraft is broken down into 7 subsystems. We have the power, structure, propulsion system, GNC, communications, solar imaging, and data handling. The propulsion system is further broken down into the component level, the main tank, the valves, the thruster, the nozzles, and even the propellant. This breakdown is done so that we can use this in the parametric modeling, so that we can mathematically analyze our system to ensure that different requirements are being met. Here's just a sample of the parametric modeling that is done. We have a mass balance of the overall system. We also have the fuel capacity equation to make sure that there's enough fuel in the main tank to meet the mission delta V requirements. So this is the sort of modeling that we're doing with the subsystem breakdown.
Hello, my name is Asael, and I'm going to be talking about how our team generated feasible alternatives. So the method we chose for generating our feasible alternatives is called the morphological chart, which is a table. What the table set up is that we split up our system into subsystems and came up with up to 6 different ways to make that design for that subsystem. So the 3 alternatives that we were able to generate from the morphological chart were the alternative 1, a Mars-line outpost, the tri-point constellation, and the heliocentric pathfinder. In this slide, you can see that how we use the morphological chart to generate the alternative. So, and highlighted in yellow are all the places where we made the design choice that could get to this first alternative. So alternative 1 is Mars-line outpost, and it is a single spacecraft on the Sun-Mars L1 position. So it has continuous sun observation, and it can sample remotely and in situ. Highlighted in green is how we generated the alternative for tri-point constellation. So alternative 2 is the tri-point constellation, and it has 3 mini-sats that are located at the Sun, Mars, L1, L4, and L5 positions, and they can gather data in situ and remotely. And as well, it has they have onboard AI that can classification for the data that can process it, essentially. Highlighted in blue are the design decisions that were used to generate alternative 3, the heliocentric pathfinder. So the Pathfinder is in the Mars Trail orbit, and it's a CubeSat that can only gather data in situ, and it's more so like for a smaller scale mission. So now I'm going to go into the methods for how we evaluated the alternatives. So low-level design decisions are very dependent on which concept is chosen. So we made concept selection at the system level, and the way we went about that is using trace studies. And trace studies, the trace study we used was based on the weighted decision matrix, where we scored every concept 1 through 5 against 8 different weighted criteria. And the criteria were the power system, payload, communications, propulsion system, structure, positioning system, developed technology, and mission requirements. So after the trace study was concluded, these are the sum of the scores. So in the table, you can see that the winning score was 4.35 for the tri-point constellation. That means that this was the best design choice based on our weighted criteria, and followed so closely behind by the Mars-line outpost. Here is the concept drawing of our final concept, SOLACE. SOLACE stands for the Solar Observation Laboratory for Active Warning of Coronal Explosions. And this is a set of 3, so these are 3 identical spacecrafts that can all do the same observations. So SOLACE is a 3 spacecraft constellation with 3 identical mini-sats located at the Sun, Mars, L1, L4, and L5 positions, and they have the same payload capacities and capabilities. So they're both set up for remote sensing using magnetometers and in situ sensing using coronagraphs and other plasma imagers. And the systems also have an onboard AI system for handling data and processing.
Okay, so now going into some of the higher level risks. The trend here is that most of these are unlikely to occur, but the impact is a little higher. And again, these are just higher level risks that we've considered, such as missing a launch window or not having enough propellant, and we have mitigation strategies in place for all of these. In conclusion, SOLACE is a unique, first-of-its-kind mission that has been specialized to meet both stakeholder needs of monitoring the sun while also providing early warning of space weather events. And we have gone through the risks and alternatives and believe that this is the best mission design. These are some references. Thank you for your time.